When you leave your local area and fly cross-country, you have a choice of using one of several forms of navigation. In this program, we'll look at two of these, pilotage and dead reckoning. When you use pilotage to fly a predetermined course, you'll identify features on the ground by comparing them to symbols on an aeronautical chart. The recommended chart to use for cross-country flights is a sectional, since it provides more detail than other types of charts. Always use a current chart for flight planning and navigation. An out-of-date chart may give you incorrect information. The altitude you select is also important when you need to identify landmarks. If you're too high, detail is lost, and some checkpoints may appear too small to be positively identified. Flying too low not only gives you a poor perspective, but may restrict your visibility, especially when haze and smoke are present. The key to pilotage is selecting reference points along your route that are easy to identify from the air. Let's look at some examples. Lines that intersect or that form unusual angles are good checkpoints. Here, the jog in the road just before the intersection makes it easier to identify from the air. When you identify a checkpoint, use more than one feature. Here, the town of Windsor can be identified by the angles formed by the road and railroads to the east. In addition, there's a lake to the north and a tower to the south. When you combine all of these items, your identification of the checkpoint becomes much easier than if only one feature is used. As you gain experience, maintaining orientation by reference to landmarks will become second nature. Taking the time to adequately plan your flight will help you maintain orientation over unfamiliar or featureless terrain. When you combine your pilotage skills with dead reckoning, you have a very precise form of navigation. As with pilotage, preparation for dead reckoning navigation begins prior to flight, when you use time, speed, distance, and direction to predict the movement of your aircraft along the planned route. Thorough pre-flight planning is the key to a successful cross-country flight. You'll usually begin with an analysis of the route. In this step, you'll determine the true course, measure the distance, and select prominent checkpoints. To find the true course, you'll use a navigation plotter similar to this one. It has three basic components: a straight edge to draw the course line, a protractor to determine the direction of the course, and mileage scales to measure distance. To help demonstrate the use of the plotter, we'll use this simplified rendition of a sectional chart. The departure airport in this example is McGee, and the destination is Waynesboro. The straight edge portion of the plotter is used to draw a line connecting the two airports. This is what's referred to as a direct route. To measure the true course, select the line of longitude that's close to the midpoint of the route. Then align the straight edge with your route and place the small hole over the longitude line. Read the true course where the line of longitude crosses the protractor. Use the scale with the arrow pointing in your direction of travel. In this example, the true course is 102 degrees. The outer scale on the protractor represents easterly courses, and the inner scale represents westerly courses. If your course does not cross a line of longitude, you can use a line of latitude for the measurement. The small north-south scales are used instead of the larger east-west scales. In this example, the true course is 30 degrees. Another function of the plotter is to measure distances. Most VFR plotters have mileage scales that match WAC charts, as well as sectional charts. This plotter also has a scale to be used on terminal area charts. Always use the scale appropriate to the chart you're using. Both nautical and statute mile distances can be determined with the plotter. Let's look at how to measure the mileage for the sample flight. To measure the distance from McGee to Waynesboro, place the zero end of the plotter over the departure airport and align the straight edge with the course line. In this example, the nautical mile scale is used. The distance to the destination airport is 60 nautical miles. Now that the course is plotted and measured, return to the actual chart and select checkpoints that will help you identify the course during the flight. The number of checkpoints you select depends on the length and complexity of the flight, as well as the terrain you're flying over. Each checkpoint should be clearly marked on the sectional chart and entered on a navigation log. This log is an excellent tool for organizing all of the data about the flight. The information recorded so far includes the checkpoints, the route, which in this case is direct, the total distance, and the true course. The analysis of the route should also include measuring the distances between each checkpoint. The next planning step is to analyze the effects of wind. Here you need to determine the wind speed and direction and the true airspeed. With this information you can find true heading and ground speed. You can obtain the wind information during your normal pre-flight weather briefing with the flight service station.
Wind and temperature at 3,000 are forecast to be 240 at 16 and temperature 23. At 6,000, 230 at 20, temperature 17.
The analysis of the winds aloft will usually reveal the most favorable cruising altitude. The altitude you choose should comply with the VFR cruising altitude specified in the FARs. The altitude is also important for determining the true airspeed for the flight. This airspeed may be found in the pilot's operating handbook or by using the flight computer. With the wind, true airspeed, and true course known, you can use the flight computer to find true heading and ground speed. To compute these values, you'll use the same procedures as described in the program on flight computers. To conclude the direction calculations, convert your true values to magnetic by adjusting for variation and deviation. Lines of variation are printed on sectional charts and are labeled in degrees west or east. When you apply variation to the true heading, westerly values are added and easterly values are subtracted. This line represents 2 degrees easterly variation. Therefore, you will subtract it from the true heading of 107 degrees to get a magnetic heading of 105 degrees. A good memory aid on whether to add or subtract variations is east is least and west is best. Now you are ready to adjust the magnetic heading for deviation by compensating for the instrument and installation errors in the magnetic compass. This card tells you what heading you should steer for a particular magnetic heading. The magnetic heading for this flight, 105 degrees, falls between east and 120 degrees. Since neither of these headings require a correction, the compass heading will be the same as the magnetic heading. As a final step in the route planning, compute the time and fuel requirements for the flight. These are basic time, speed, and distance calculations to find the estimated time en route, ETE, between checkpoints and the total estimated time for the complete trip. The fuel requirement should also include the reserve required by the regulations. Spaces are provided on the navigation log to record pertinent information about departure and destination airports. The sources of this information will be covered in the next program. A flight plan form is also included on the reverse side of the navigation log. This form contains spaces for you to list pertinent information about your flight. When you have completed the form, you should file the flight plan by calling the nearest flight service station.
I'd like to file a VFR flight plan.
Go ahead.
The aircraft is 52241, a Cessna 172/uniform. True airspeed 112 knots. Departure point is McGee. Proposed departure time 1600 Zulu. Altitude 3,500. Route is McGee, direct Waynesboro. Destination Waynesboro. ETE 31 minutes. Fuel on board 3 hours 40 minutes. And the pilot's name is Fred Adams. 1114 Fox.
If you anticipate a delay in your departure in excess of 1 hour, let the flight service station know. If you do not, the flight plan is considered void after an hour and you must refile. One of the most satisfying aspects of learning to fly comes from completing a well-planned cross-country flight. As you gain experience, you will find that the fundamentals learned during pilotage and dead reckoning can be applied to most other forms of navigation.
As you saw in the last volume, basic navigation involves using visual checkpoints and time, speed, and distance calculations. In this volume, you will be introduced to other forms of navigation that use aircraft radios and ground transmitting stations. The first form of radio navigation we'll look at is the VHF omnidirectional range, which is commonly referred to as VOR navigation. A VOR station continuously sends out signals that are received by a radio in your airplane. The station is shown on an aeronautical chart by a compass rose surrounding its location. The compass rose is a graphic depiction of the signals transmitted from the VOR. These signals, called radials, extend out from the station and are numbered clockwise from magnetic north. Although the number of radials is infinite, only 360 are used. Their directions are indicated by numbers on the outside of the compass rose. Your position in relation to the VOR is usually expressed in terms of the radial on which you're located. Here, for example, the airplane is on the 090-degree radial. To receive the signals transmitted by a VOR station, you need certain airborne equipment. The antenna picks up the signal and relays it to the VOR receiver. Here it is interpreted and then sent to the VOR indicator, where the signal is displayed as navigation information. This visual display has three components. They are the course selector, the course deviation indicator, and the to from indicator. The course selector, also known as the omni-bearing selector, or OBS, allows you to set the desired course. The numbers and tick marks on the VOR indicator ring correspond with the numbers on the compass rose of a sectional chart. The course deviation indicator, known as the CDI, helps you determine your position relative to the course. If the needle is centered, your airplane is located on a radial. If the VOR indicator is set properly, the to from indicator tells you whether your selected course will take you to or from the VOR. When you see an off or nav indication, one of two situations has occurred. Either the signal is too weak to use for navigation, or you have just passed over the station. Now that you have a basic understanding of the VOR components, let's look at how to put them to practical use. The first step is to select and tune in an appropriate facility. Station information is represented on an aeronautical chart by a box located near the compass rose. This box includes the name of the VOR, the three-letter identifier, the Morse code identification, and the station frequency. To use it for navigation, your first step is to enter the frequency into the airplane's receiver. Turn the frequency selector knob until 117.5 appears in the display window. On this receiver, the frequency is set in the standby window, then transferred to the use window. Always verify that you have tuned in the correct frequency and that the station is in service by listening to the Morse code or voice identifier. With the station tuned and identified, it is easy to determine your position. Simply turn the OBS knob until you get a from indication. Remember, radials go out from the station. Continue turning the knob until the CDI centers. The number under the index is the radial on which you're located. Keep in mind that this display tells you where you are in relation to the station and not to the heading of the airplane. Here, for example, the airplane is located on the 070-degree radial from the station. The airplane could be pointing in any direction, and the VOR indicator would still read the same. However, the heading in relation to the VOR indicator does play an important role when you want to fly toward or away from the station on a specific radio. To fly away from the station on the 070-degree radial, all you have to do is turn the airplane until the heading indicator and radial under the index are in agreement. With the from indication and the needle centered, you'll fly away from the station on the selected radial. If you want to fly toward the station, rotate the OBS until you have a to indication. When the needle centers, note the number under the index. This is the magnetic heading to the station. Now turn the airplane until the heading indicator and radial under the index are in agreement. With the needle centered and a to indication, you'll fly toward the VOR. It's important to remember that when the VOR and heading indicators are in agreement, a to indication will take you toward the station, while a from indication will take you away from the station. This assumes that there is no wind to drift you off course. The CDI is the component on the VOR indicator that provides wind correction information. If you drift off course, the CDI will point in the direction of your desired course. A good way to visualize your position is to picture the airplane at the bottom of the VOR indicator. If the needle is to the left of the airplane, your course is to the left, and you need to make a heading correction to the left to get back on course. If the CDI moves right of center, your desired course is to the right, and you need to make a heading correction to the right. The dots along the bottom of the VOR indicator show you how far you are off course. Each dot represents 2 degrees. In this case, you're 8 degrees left of course. You need to change your heading to the right to get back on course. The amount of correction you need will depend on the strength and direction of the wind, as well as your distance from the station. In this case, a 20-degree correction angle is used to regain the course. As you near the desired course, the CDI will begin to center. When you're back on course, you'll need to turn to a heading that compensates for the wind. A good technique is to use half the original correction angle you used to regain the course. In this example, you would use a 10-degree wind correction angle. If the correction angle is too great, the airplane will drift upwind. If you are close to the desired course, simply turn to parallel the radial and let the wind drift you back. A correction angle may be required if you are farther from the course. Once you're back on the radial, apply half the original wind correction angle, which in this case is 5 degrees. There are occasions when you want to track to or from a station on a different radial than the one you're following. This requires you to leave one radial and intercept another. To help explain the intercept procedure, let's assume you're tracking outbound on the 070-degree radial and you want to be on the 090-degree radial. You should first visualize where you are and where you want to go. It's a good idea to turn to parallel the new course before you make your intercept correction. This helps to ensure your intercept is in the correct direction. Now, rotate the OBS to enter the desired course in the course selector. To intercept the 090-degree radial, you'll need to turn right. Continue to fly the heading until the CDI centers. When you have intercepted the new radial, turn to a heading that will allow you to remain on course with the needle centered. The intercept angle you choose depends on a number of factors. If you're flying toward the VOR at a point far from the station, a fairly large intercept angle might be required. When you're close to the station, a shallow angle can be used. If you use a small intercept angle when flying outbound, it may take a long time to reach the new radial. Since the radials diverge away from the station, a larger intercept angle may be necessary. Although VOR navigation is quite simple, you should be aware of a few unique factors, such as reverse sensing. This happens when you select and fly on a radial that is 180 degrees from your heading. When this occurs, the information provided by the VOR is opposite the normal indications. For example, to track to a station on the 070-degree radial, you need to set 250 in the course selector, then fly a heading of 250 degrees. If you mistakenly set 070 in your course selector, then fly inbound on a heading of 250, you will experience reverse sensing. If you drift to the left of course, the CDI gives a false indication that your desired course is to the left. Based on the instrument indication, a correction in the direction of the needle causes you to drift farther off course. You can avoid the problem of reverse sensing by keeping the course selector in general agreement with your heading indicator. Another unique characteristic that you may experience is a CDI fluctuation. Certain propeller RPM settings can cause the CDI to fluctuate as much as 6 degrees. You can eliminate the problem by varying the RPM slightly. Let's take a look now at how to use the VOR to determine your exact position. You've just seen how to locate where you are in relation to the station. While this procedure allows you to determine your direction from the station, it does not tell you how far you are from the station. Assuming you are on the 300-degree radial from this VOR, let's use a second VOR to pinpoint your position. First, tune and identify a second station. Next, turn the omni-bearing selector until you get a from indication and the needle centers. The course under the index, 240 degrees, is the radial on which you are located. Plot the radials from both VORs on your sectional chart. The point where the two lines intersect is your exact position. Becoming familiar with radio navigation will enhance your basic navigation skills. The information provided by VOR serves not only as a backup to pilotage and dead reckoning, but also provides accuracy in determining course, distance, and position. In the next section, you will be introduced to the Automatic Direction Finder, commonly known as ADF. When using this navigation aid, you will be able to apply some of the techniques you learned in this section.
In the last section, we looked at how to navigate using VOR. In this section, you will be introduced to the Automatic Direction Finder, which is referred to as ADF. Several ground facilities transmit signals that can be received by your airborne ADF equipment. The most common facility is called a non-directional radio beacon, or NDB. Certain commercial broadcast stations can also be received, but they should not be used as your primary source of navigation. NDB signals are transmitted in the low to medium frequency range and travel as ground waves and sky waves. Ground waves are capable of following the curvature of the Earth, while sky waves bounce off the ionosphere and can be received over great distances and at low altitudes. These signals are picked up by the ADF antenna on your airplane and relayed to the ADF receiver. This receiver has an on-off volume control knob, a station frequency selector, and several mode selectors. These selectors allow you to perform a number of functions. For example, the mode selector labeled ADF allows you to operate in either ADF or ANT, which stands for the antenna function. This mode provides maximum sensitivity to radio signals for tuning and identifying the station. With the selector in this mode, enter the NDB frequency in the receiver. You can find station information next to the NDB symbol on an aeronautical chart. The station name, frequency, and Morse code identifier are provided in a magenta-colored box similar to a VOR information box. With the station positively identified, place the selector in ADF. This allows the receiver to relay the information to the indicator, which displays it on either a movable or fixed card. Let's look at how to interpret the fixed card indicator. The needle on the bearing indicator will move in the direction of the station and stop when a strong signal is found. The pointer of the needle indicates the bearing to the station. In this case, it's 060. The tail of the needle indicates the bearing from the station. In this example, it's 240. 0 degrees on a fixed card is always aligned with the nose or longitudinal axis of the airplane. The needle indicates the number of degrees from the nose to the station. This angle is called the relative bearing. In this example, the relative bearing is 060. If your airplane is on a magnetic heading of north, you simply need to turn to a heading of 060 degrees to fly to the station. At the completion of the turn, the ADF will be pointing toward 0, indicating the station is directly ahead. If you're flying a magnetic heading other than north, you must add your magnetic heading to the relative bearing to find the magnetic bearing which will take you to the station. For example, let's assume your magnetic heading is 090 and your relative bearing is 060. When you add these two together, you get a magnetic bearing to the station of 150 degrees. To fly to the station, in this case, you simply turn to a heading of 150 degrees. When the turn is complete, the needle on the bearing indicator will point to 0 degrees. If you keep the needle pointed to 0, you are homing to the station. In a no-wind situation, you will fly directly to the NDB. In a crosswind, you will have to make continuous adjustments to your magnetic heading to keep the needle pointing to 0. As a result, your aircraft will travel a curved path to the station. If you want to fly a straight line, you can track a course using a technique similar to the one you used in VOR. Let's look at the procedure. Let's assume you want to track on the 240 degree bearing to the station, and a right crosswind has drifted you left of course. The ADF needle will point to the station which, in this example, is 5 degrees to the right. Turn right, using an appropriate intercept angle, and maintain that heading. In this case, a 20-degree correction angle is being used. The ADF needle will continue to point to the station. With the aircraft heading 260 degrees, the station is located 15 degrees to the left of the nose. As you approach the course, the ADF needle will continue to move away from 0. When the deflection equals the heading correction angle, you have intercepted the desired course. Here, the ADF needle reads 340, which equals the 20-degree intercept angle. When you have turned back on the desired course, it will be necessary to establish a crab angle to compensate for wind, in this case 10 degrees. Since the airplane is crabbing to the right to maintain course, the ADF needle will indicate that the station is to the left. As you get close to the station, the needle becomes more sensitive. It's important not to chase the needle or make large corrections during this time. Station passage is indicated by a reversal of the needle. The procedure for tracking outbound is similar to the procedure used to track to the station. However, the wind correction angle is established with reference to the tail of the aircraft. Some of the techniques you learned in tracking can be used to intercept a particular magnetic bearing. To understand the intercept procedure, let's assume you want to intercept the 60-degree bearing to the station. Your first step is to turn your aircraft to a heading that parallels the course you intend to track. Then determine whether the station is left or right of your aircraft by noting the direction the ADF needle is deflected. In this example, the needle is deflected 30 degrees left. If you turn left only 30 degrees, you will fly to the station, but you will not intercept the 60-degree bearing. A good rule of thumb is to double the degrees the ADF needle is deflected. A 60-degree intercept angle, in this example, means you will maintain a heading of north to intercept the bearing. When the ADF needle is deflected 60 degrees to the right, which is the same as the angle of intercept, you will be on the desired track. Remember to lead your turn by a few degrees to avoid overshooting the bearing to the station. Continue to track to the station using the same procedures we discussed earlier. Until now, we have taken a look only at the fixed card ADF indicator. The only difference between a movable and a fixed card is that you can manually rotate the movable card. This allows you to place your magnetic heading under the index at the top of the indicator. In this situation, the ADF needle automatically provides you with the magnetic bearing to the station. The tail of the needle provides the magnetic bearing from the station. Sometimes, when using ADF, the signal you receive may be erroneous or unreliable. If you are familiar with some of the limitations of this instrument, you may be able to avoid or minimize errors you might encounter. For example, reception capabilities for ADF facilities can vary considerably. To be sure you're receiving reliable information, always identify the station before use, then monitor its ident feature. If your heading indicator is not properly set to the magnetic compass, you may have problems with tracking and intercepting procedures. You should monitor these instruments often to ensure that the heading indicator has not precessed. Other phenomena that may cause erroneous readings in your ADF are twilight effect, thunderstorm effect, precipitation static, shoreline effect, and terrain effect. You'll learn more about these when you read your private pilot manual and study the operator's handbook for your ADF. ADF is just one instrument in your total navigation system. In many cases, it's possible for you to navigate using ADF alone. However, it is generally used with other instruments, such as VOR. In the next program, we will expand on the information already presented and see how it relates to advanced navigation.
Besides VOR and ADF, there are various types of advanced navigation systems and indicators available. Our purpose in this section is to introduce you to some of them and describe their capabilities. The first system we'll look at is area navigation based on signals transmitted by VORTAC, or VOR DME stations. As you learned earlier, VOR provides for navigation between stations. But VORTAC-based area navigation allows you to fly directly to your destination, often with considerable savings in time and operating costs. To accomplish this, a course line computer allows you to electronically relocate or offset navigation aids to a desired radial and distance from the original location. These offset stations are called waypoints. For example, assume you're planning a direct flight from Storm Lake Municipal Airport to Algona Municipal Airport, and you're using area navigation equipment. The first thing you must do after determining your route is to select the closest VORs to your flight path. In this case, they are the Spencer and Fort Dodge nav aids. Then establish waypoints along the route and determine the radial and distance each waypoint is from the VOR. Waypoint number 1 is 27 nautical miles from Spencer on the 140-degree radial. Waypoint number 2 is on the 335-degree radial, 23 miles from Fort Dodge. These values are then entered into the receiver prior to your departure. Now you can simply fly from waypoint to waypoint until you reach your destination. Your course information is displayed on the VOR indicator just as it is in normal VOR navigation. If you drift off course, the CDI points toward the desired course. However, the deviation is indicated in nautical miles instead of degrees. The mileage that each dot represents is determined by the manufacturer. Now let's look at another form of area navigation called long-range navigation, or Loran. This system also lets you fly directly to your destination, but with Loran, you don't have to create waypoints. Instead, it uses a network or chain of stations which transmit low-frequency signals in the 90 to 110 kilohertz range. These low-frequency signals follow the contour of the Earth in the form of a ground wave and have a reliable reception range of 600 to 1,200 nautical miles. Loran transmitters can also produce sky waves which increase the reception range, but these signals are not considered reliable for navigation. In a typical Loran chain, there is a master station and 2 to 5 secondary or slave stations. The master station first transmits a coded pulse group. Then, each secondary station transmits its pulse at a specific time interval after the master pulse. A Loran receiver in the aircraft determines your position by measuring the time difference between the receipt of the master pulse and that of the secondary stations. Your position is then translated into latitude and longitude values and displayed on the receiver. After you enter the destination, the receiver displays course and distance to the specified point. During the flight, it provides a continuous update of the information. Because Loran operates in the lower frequency range, electrical disturbances such as lightning and precipitation static can cause signal loss or distortion. For this reason, aircraft with Loran units should have static discharge wicks and bonding cables to help dissipate any static buildup. Another limitation is the variation in speed at which the radio signals travel. The surface type, foliage, and seasonal changes can affect the speed of the radio waves and decrease their accuracy. There are several types of Loran units available, and their capabilities vary considerably. Besides bearing and distance, some receivers provide wind direction and velocity, fuel consumption, and other types of information. You can determine the features and limitations of the particular unit you're using by referring to the owner's manual or to placards located on the instrument panel. Another type of navigation that is quickly replacing traditional ground-based navigation systems is the Global Positioning System, or GPS. This type of navigation system relies on signals received from satellites to calculate the position of the aircraft. A GPS receiver determines an aircraft's position through triangulation of distance measurements from a minimum of 3 satellites. And because this system is satellite-based, it doesn't have the limitations that a ground-based system might have. It provides the same benefits as other point-to-point navigation systems, but with unmatched accuracy. 95% of the time, lateral position accuracy is within 100 meters of the true horizontal position. GPS receivers incorporate a wide array of navigation capabilities that help increase situational awareness, such as moving map displays and the ability to select the nearest airport. With such a wide variety of manufacturers and options comes the responsibility to understand the operation and limitations of the system you use. Your pre-flight preparation should include a review of GPS and how your particular system functions. GPS units come in both panel-mounted and handheld units. Handheld units are meant only for flight under VFR conditions and are not certified for use under IFR conditions. Each GPS unit has a different type and location of the receiver antenna. Panel-mounted GPS units have permanently affixed antennas. A handheld unit, however, may have a self-contained antenna or a detachable antenna. You need to make sure these antennas are in a location that provides adequate signal reception. It is also your responsibility to verify that a panel-mounted unit has been properly installed and maintained in accordance with the AFM or POH. You should also be aware that GPS systems utilize Receiver Autonomous Integrity Monitoring, or RAIM. RAIM checks the integrity of the navigation solution and alerts the GPS user to a position error. Many handheld GPS receivers do not have RAIM alerting capabilities. These receivers should not be used as the sole system of navigation. Instead, you should integrate GPS with other forms of navigation such as VOR, pilotage, or dead reckoning to ensure navigation accuracy. Most GPS units include a navigation database. Flying with an outdated database is like using an expired sectional chart. In fact, to fly IFR by GPS, you must have a current, updatable database. Since both airspace and navigation data are constantly changing, you should apply this requirement to VFR GPS use as well. GPS is rapidly becoming the standard means of navigation. Take the time to become familiar with the unit you will use, planning your flights carefully prior to departure, and when possible, programming your GPS on the ground. In addition, always check NOTAMs for any outages in the GPS system that would affect GPS navigation. Another way to increase your navigation capabilities is through use of specialized instruments. One such instrument is the Horizontal Situation Indicator, or HSI. It combines the functions of two instruments in one display. Its movable compass card works like a heading indicator to give you magnetic heading information. The other elements work like a VOR indicator to help you maintain your orientation to the station. Let's take a look at the components to help you understand the capabilities of HSI. A heading select bug is an index that rotates when you turn the heading select knob. If an autopilot is engaged, the airplane will automatically turn to the heading you select with the bug. If an autopilot is not used, the select bug serves only as a reference marker as you complete the turn. Like the CDI, the lateral deviation indicator tells you if you are left or right of course. When you are on course, the needle is aligned with the course arrow and the reciprocal course pointer. The ambiguity indicator works like a to/from indicator to tell you if you are flying to the VOR or from it. One other feature that HSI provides is glide slope information, which is used during instrument approaches. You may learn more about this if you proceed with additional pilot training. Now let's look at another advanced instrument, the radiomagnetic indicator, or RMI. The RMI combines the functions of three instruments: the heading indicator, the VOR indicator, and the ADF indicator. The slaved compass card automatically displays your magnetic heading at the top index. Typically, the single needle indicates the magnetic bearing to the VOR station, while the double needle shows the bearing to the NDB. The tail of each needle indicates magnetic bearing from the station. With the needles indicating the bearings to separate navigation aids, constant position orientation is provided. You can track toward one facility while monitoring your progress on another. The information presented in this section is intended to serve only as an introduction to advanced navigation. Be sure to refer to the operating handbook for details on the system you are using.